In this video, I'm going to talk about linear transformations and what makes a function a linear transformation. I'm going to assume that you've already watched those 3 videos from 3 Blue, 1 Brown. That is linear transformations in 2 dimensions, linear transformations in 3 dimensions, and linear transformations between 2 and 3 dimensions as a background for this video. So if you haven't done that yet, I recommend watching it first. Otherwise, some of what I say won't necessarily make sense. Before we dive into linear transformations, I wanted to talk a little bit about function notation because it'll help our conversation go a lot smoother and it'll allow me to write things in a much more clear and concise way when I write things on my iPad. So function notation that you learn in algebra and calculus is a bit lacking in detail for a good reason. So for example, kind of a classic function that you may have encountered is something like f of x equals x cubed, or sorry, it doesn't matter what this function is, x cubed minus x plus 3. And if you were dealing with this function in an algebra course or a calculus course, you might just write this and everyone knows what we're talking about. But there's another way we could write this that includes a little more detail. I can write something like this. And what this is saying, if I read this across, this says f is a function from the real numbers to the real numbers. So I've started by specifying what is the domain, what are my inputs, what is the codomain, what are my possible outputs. And then this next line is telling me where to send anything. This is saying that x is mapped to x cubed minus x plus 3. These 2 pieces of notation represent the exact same function. This one just has more information about what the domain and codomain are. And I want to give you a second example to illustrate why this matters, and it'll be an example from this course. If I write something like this, t of v equals 2v, you should immediately believe that this is a function because you know that we're dealing with a vector, we can multiply it by a scalar. But it's not really clear where this vector should come from. So this is ambiguous. I haven't really defined a function in that I haven't told you what inputs are allowed. And so it would be better to write something like, okay, t is actually a function from R4 to R4 that takes a vector v and multiplies it by 2. Here, this function notation was totally fine if you're in a calculus or an algebra course because all of your functions essentially are taking real numbers as inputs and giving real numbers as outputs. And so there's no problem with writing things like this. It's not bad. It's just when you get into a course like linear algebra where we're considering lots of different vector spaces, or as you take more math courses, a lot of the value of math is that it generalizes to lots of situations. We don't want to only assume that someone knows what output and input spaces we're dealing with. And so I'll often write this notation, although if it's unambiguous from the situation, there's nothing wrong with this sort of notation. Okay, so this is function notation that I'll use throughout this video. If you haven't seen this, what I'd say is it's one of those notations that you'll become familiar with, right? It's just because it's new if it's confusing. Once you see a few examples, it should become clear. All right, so let's move on to linear transformations. In the 3 Blue, 1 Brown videos, they're great videos, but they only talk about 2 and 3 dimensions. And in those videos, the way that they define a linear transformation is as something, it's a function that leaves the origin where it is, right? It doesn't move the origin, and it might rotate space, it might stretch space, it might flip space, but it never bends any straight lines. So linear transformations are functions that leave the origin in place and don't bend straight lines. And this is right in some sense, right? This is how you should be thinking of linear transformations. They're these nice functions. They don't do anything crazy. They don't move stuff all over the place. They're really just stretching and rotating and maybe reflecting space. So this is great, but there's 2 problems with this, or maybe 3. depending on how I count them. One is that this kind of starts to fall apart as you move to higher dimensions a little bit, right? So this function here that I've defined, this function t, is a linear transformation, but it's from R4 to R4. And so not being able to visualize R4, what does it really mean that it's not bending any straight lines? This isn't necessarily so bad, because as I've talked about, we can think of higher dimensional space by pretending it's lower dimensional space. So we could, think of this as behaving like a linear transformation from R3 to R3, for instance, but still we're losing something there. So that's one issue. We can move up to higher dimensions. Another issue is we want to deal with other vector spaces. So what about this function that I'm going to call d for a reason that I think will become clear, which is going to take polynomials of degree 3 or less and map them to polynomials of degree 2 or less. And what it's going to do with some polynomial is it's going to send it to its derivative. So this is definitely a function, right? If you think back to calculus, when you take a polynomial and take its derivative, you reduce the degree by 1. And so if we start with polynomials with degree at most 3, we end up with polynomials of degree at most 2. So it's a function, but what does it mean to say this is linear? It is linear. And I'll talk about this in a second, but what does that mean? What does it mean? It doesn't, are we going to say, oh, it means that it doesn't bend any lines? We're talking about polynomials. What is a line of polynomials? So this is the second issue with that definition of linear transformations, is that it doesn't really generalize to other vector spaces that aren't Rn. And then the final thing is that visual definitions, intuitive definitions of things often don't work well in calculation. And oftentimes for calculational purposes, it's useful to have symbolic explanations for things. And so I want to talk about what does it mean symbolically for something to be a linear transformation. And I'll define this in generality. So I'll slowly show this. If V and W are vector spaces, and we have a function from V to W, what does this mean for it to be a linear transformation? So these vector spaces, if this is seeming a bit abstract, you could call them R2 and R3, or you could call them R7, or you could decide that they're any vector space. A linear transformation is going to be a function so that there's two things that will happen, and I'll just scroll all the way down so we can see this better. If we plug in a sum of two vectors to the function and see where it gets sent, that gives us a vector in W. That's going to be the same as initially plugging vector 1 into the function and separately plugging vector 2 into the function and then adding them. Or in other words, we can either add the vectors first and then apply the function, or we can apply the function to each vector and then add those resulting vectors. Either way, we get the same thing, no matter what two vectors we start with. It will also need to do something similar with scalar multiplication. If we start with a constant times a vector and plug that into the function, that's going to be the same as if we plugged the vector into the function and then whatever we got out, we multiplied it by the constant. One way we say this is, this first property we say is that the function respects addition, and the second property says that the function respects scalar multiplication. And as you see more and more math, you'll start to see these sorts of things, that anytime we're studying a mathematical object, something with properties, something with operations on it, we're often interested in the functions that retain those properties. So with vector spaces are things where we can add and multiply by scalars, and the functions that will be useful for us are the functions that respect those things. And what that means is these two properties. That is, doing the operation and then applying the function is the same as applying the function and then doing the operation. All right, so this is pretty abstract, I think. And I want to actually just give you an example that this is not usually what I would do. Usually I would give you an example in Rn. But since I know that most or all of you have taken calculus, I want to talk about the derivative, because the reality is that every single person who has passed a Calc 1 course knows that the derivative is a linear transformation. They just don't know those words. That is, these two properties of the derivative are the main properties that you use in calculating derivatives. Every single derivative you calculate, for the most part, you have to apply these properties. And what I mean by this is that if you have a derivative, let's use that function that I wrote up earlier, and you take this derivative, you might just do this all in your head. But the way that you take this derivative is you first say, hey, this thing respects addition. I can split this up over addition. And you say, oh, this also respects scalar multiplication. So this negative sign I can pull out. And then you get the answer, right? 3x squared minus 1. And again, you might just do this in your head, right? If you're in a calculus class, you hopefully get to the point where you look at this and go straight to here. But what you're doing in your head is treating it piece by piece and treating any sort of scalar multiplication as something that you can just deal with later. And that's what it means for this to be a linear transformation. It's saying we can apply the derivative to the whole thing, or we can apply it piece by piece, including pulling out scalars, and we'll get the same answer. So this is what it means for something to be a linear transformation. And this is nice because this definition works for all vector spaces, right? I didn't say anything special about Rn or about polynomial spaces. And it matches up with this intuition that it doesn't move the origin and it doesn't bend any lines. And it's not necessarily obvious that this is true in R2 or R3, but I think it's at least believable that when you have this really nice structure, that it doesn't mess with addition and it doesn't mess with scalar multiplication, and you think about the fact that lines are really just scalar multiplications and additions, I think it's very believable that this sort of property would give you a function that doesn't bend any lines. So the final thing that I want to mention in this video about linear transformations is that it turns out, maybe unsurprisingly, hopefully as this starts to happen in this course, linear algebra is one of the most connected math courses that I've ever taught, if not the most. That is that everything we do seems to keep coming up over and over again. And we started this course with linear systems, and now we're talking about linear transformations, and let's see how these things are connected. Because it turns out there's very deep connection between linear transformations and linear systems. So far, we've seen that when we have a linear system, so here's an example of a linear system, we can rewrite it as a linear combination of vectors, or in vector form if we want. And so this is this linear system written in vector form. And if you're kind of trying to remind yourself of this, we talked about this when we first introduced vectors. It was one of the ways that we explained why vectors are useful. And if you recall, when we started studying independence of vectors, linear independence, and span of vectors, this was really useful because we realized that if we're talking about questions of linear independence, we could translate back to a linear system and say, well, this is really a question about solutions to homogeneous systems. And questions about span, again, we went back to a linear system and said, oh, this is really a question about a linear system where we're wondering what vectors we can actually get a solution to when we put those coefficients in the right-hand sides of the equations. So it was actually really useful to think of this linear system as also being written in vector form. The 3 blue 1 brown video talks about this notion of a matrix times a vector as representing a linear system. And I actually talk about this in a later video. So it's not the best order of things. But so if you don't fully understand what a matrix times a vector is, that's fine. Right now, if you're looking at this and you're thinking we're skipping ahead, that's going to be totally okay. I wanted to mention this now. We can rewrite this whole system as a single equation of one matrix times one vector being equal to another vector. So the matrix is going to be the coefficient matrix of the left-hand sides of the equations. So you can think of this as all of these coefficients placed into here, or equivalently, it's just all the vectors here as the columns. So that's our matrix A. Our matrix X is going to be just a vector of all of our variables. And our matrix B is going to be just a vector of the right-hand sides of the equations. And then all of this is equivalent, this whole system, to A times X equals B. And if you know what a matrix times a vector is, you should write this out and convince yourself of it. And if you don't know what it is, that's fine. Just maybe come back to this once we talk about matrix times vector. This is going to be really powerful because as we saw with writing a system in vector form and that allowing us to study vectors, we're going to actually get two things here. It's going to be really useful in terms of studying matrices. So we're going to work more with matrices, which are related to linear transformations. When we're studying matrices and linear transformations, it's often going to be useful to remind ourselves, hey, wait a second, these things are really just linear systems in some way. Thinking of them as linear systems will allow us to understand and study their properties using linear systems. But then conversely, it'll go the other direction. As we learn stuff about matrices and linear transformations, we'll realize that we can apply those things to solving linear systems in ways that can make solving linear systems either easier or more efficient, or just it'll make things about linear systems make more sense. So it's going to be really useful to think of all of these things as connected to each other.